Hello, thank you for joining us. My name is Nathan VanHoudnos, and I'm here to talk to you about train but verify. But first, a word from our lawyers. This basically says that everything in this presentation is publicly releasable. So before I start explaining about train but verify in this particular project, what I want to do is I want to kind of come up a couple of levels. And I want to introduce this concept of AI engineering. AI engineering is a field of research and practice that integrates a lot of different pieces of expertise: software engineering, systems engineering, computer science, human-centered design. And the idea is to build AI systems that are responsive to human needs and mission outcomes. Why do we need a field of AI engineering? Well, some research that's been done suggests that about 85% of AI deployments will in fact fail. And the reason that they'll fail, in some sense, is because people are making heroic efforts to solve problems, but they don't have a defined and repeatable system to make sure that they can achieve their goals and understand how to avoid failures. So that's AI engineering. It has three different pillars. One of them is human-centered, in that it works with and for people. Another is that it's scalable in terms of both very large models and very small models at the edge, and also that it's robust and secure, which means that it's reliable when under uncertainty or threat, right? And train but verify is in fact about threats, right? What are the threats to machine learning models, and how do we make sure that we can overcome those threats? So let's talk about threats for a minute. When I like to introduce machine learning threats to people, I like to think of the Beeler Taxonomy, which is basically saying that an adversary can make a machine learning component either learn the wrong thing, do the wrong thing, or reveal the wrong thing. And what I've listed under here for the different pieces is that for learn the wrong thing, what you have is the original Badnets paper for label poisoning. For do the wrong thing, what you have is this idea of like a facial recognition system that then, if you put on glasses that are specially designed, you can fool that facial recognition system, so you can fool it in operation with an adversarial example. Or revealing the wrong thing, where after you have a trained model, you can back out characteristics of the training data. In the specific example, what you have is you have person Z extracted out of the model, and you can in fact see that those are the same person. Okay, so those are roughly the three different threats. So in the train but verify project, what we do is we think about it a little bit more broadly. Right? We want to make sure that we can train to enforce a learn policy. We want to make sure that the systems learn the right thing. And then if we train to do that, we want to go ahead and verify that they did learn the right thing. Similarly, to make sure that they don't do the wrong thing, to not be fooled by adversarial attacks, right? Then we need to verify that they are in fact not fooled by adversarial attacks. And similarly for reveal, right? And there's a lot of work that focuses on a single security policy at a time, where if you're checking against data poisoning, you're going to verify that you weren't poisoned. If you're checking against robustness to adversarial examples, you're going to verify that your adversary can't actually fool you in practice, right? If you're checking that you're not revealing secrets, or if you're trying not to reveal secrets, you're going to check that you're not going to reveal secrets. But what if you need to do two things at once? So for example, the DoD makes high-stakes decisions and also trains on sensitive data. And so what about this cell of this train but verify grid? So it's been known for a long time that defenses for do policies reveal information about the data. So for example, in the original Cypress et al. Paper, where they showed that adversarial examples against robust models end up looking like instances of the class that is being targeted, right? We've known that these robust models might be leaking information about the training data. And so to explore this a little bit, let's just look at two models, a standard model and then a model that's trained with projected gradient descent, right? And so on the y-axis, what we have is accuracy, and on the x-axis, what we have is the strength of the attacker, as the attacker is allowed to add more and more and more noise, their perturbation budget. And so what we see here is that standard models, as soon as you add a little bit of noise, their accuracy just craters, right? And then it just stays bad as you add more and more noise to the model. Robust models, however, more gently and smoothly degrade, But what happens is now the adversarial examples end up looking like the target class. So here, they begin to look like ships. And so what you can do is if you take a model that's been trained on ImageNet in a robust way, and then take out and then extract these adversarial examples, and just kind of move from class to class to class, what you get is this video on the top, where what we have is we have adversarial examples that are revealing information about the training data, because these things actually, in fact, look like the different classes, right? Like that's the alter class, for example, and it looks like, sure, it does look like alters, and the dogs look good, and the insects look good, and all of that kind of thing, right? So we're actually leaking information about the training data. In contrast, examples extracted from undefended models look basically like noise. And so what I want to do next is I want to just sort of meditate on this idea of what information can be revealed by a model and sort of walk you through it. So imagine that, well, so not imagine, this is in fact the example from the stingray class, right? What we see here is we see what looks like a stingray, it looks like a stingray pattern. It's in the water, and then we have this object over here, which looks maybe like a swimmer in the water. And so then if you go into the ImageNet training data, you can in fact find lots and lots of examples of people in the water with stingrays, right? So here's the adversarial example for cauliflower. And I look at this and I'm like, huh, the colors might be wrong because the cauliflower is purple. But of course, actually, if you're more of a foodie, you'd know that there is in fact lots and lots of purple cauliflower, and it's in fact very well represented in the ImageNet data set if you actually go into the data and inspect the training data itself. Right? So you can learn things about the data by looking at the adversarial examples from robust models. Let's give a more in-depth example. So let's look at the street sign class. So here's the adversarial example for the street sign class. And I look at that and I say, huh, that looks maybe like E10. OK, let's go to Google Maps. Let's throw in E10. Oh, it looks like E10 is in New York. There's actually a whole bunch of stuff in New York. Let's go to Google Street Maps view. It looks like that. Huh, that looks like maybe a New York style street sign. And if maybe you thought it was E70, same thing happens, right? So then what we can do is we can go into the data set and we can see, yes, there are actually quite a few photographs with these New York style street signs in the data, right? So we're revealing what kinds of, in this example, street signs are present in our data by looking at the adversarial examples. Okay, so let's make this a little bit more concrete for the DoD, right? If we're going to have AI engineering, and specifically we're going to have secure AI engineering, then what we need is we need to defend from multiple attacks. And the problem here is that state-of-the-art methods to enforce doing the right thing can leak information about the training data, right? Here are some examples of the aircraft carrier class and the submarine class, right? That are revealed in the robust model but aren't revealed in the standard model, right? And so what I want to point out here and argue for is that a defended model may, in fact, unintentionally reveal critical information about the data, specifically its sources and its methods, right? So to give a very sort of open example, right? What if we wanted to keep confidential that the way that we collected the information for a particular class was from personal photos, right? So that's with the stingray stuff, we train our defended model, and now our adversary is able to find out that there were people in the training data, right? A characteristic of the sources and methods of the data, right? And so organizations with high-stakes systems trained on sensitive data need new defense methods. We need to make sure that we can do things correctly and to not reveal secrets, okay? That's basically right where the Train but Verify program is. And what have we been doing up in 2021? What we've been doing is we've been trying to quantify attacks to reveal policies, develop new methods for due defenses and due attacks, develop new methods to verify those policies, and also release AI engineering tools, right? Because where we're eventually going with is that after we can better measure how information is in fact leaked, right? And we have the state-of-the-art for how to defend against doing the wrong thing, right? Then we can actually give some advice about how to both not leak information and do the right thing, which is our goal for next year. So what I'd like to do is we've got a lot of papers under review. I'd like to go over our ICML 21 paper on globally robust neural networks as a sort of a deep technical dive. This work, the first author on this is Klaus Lino. You'll see his picture at the end of the slide, or at the end of the deck. Okay, so globally robust neural networks. What are we talking about? So first, let's think about we have a model. Let's just call that model F, and let's define this local robustness condition, right? And so what's happening is that if you have some piece of data in pixel space and you draw an LP ball around it, right, that has radius epsilon, as long as it's far enough away from the decision boundary, at least epsilon away, then it has to have the same classification, right? So it's locally robust if decision boundaries don't ever cut in to LP balls. And that's how, like, Madry's adversarial training works. That's how trades works. That's how a lot of things work, is they try to penalize this idea of crossing a decision boundary in an LP ball. Okay, now that's really low level. That's really zoomed in. So let's zoom out for a minute, right? And let's think about a notion of global robustness, right? And so what I've drawn here on the slide is I've drawn this sort of half-moon spiral data set where we've got some dark things that curve around like this. This is one of the classes. And then we've got some lighter stuff that curves around like that. That's another one of the classes. And then we have a classifier that's trying to pick between those two colors. And the way that we drew this particular classifier is that it has a super, just really thick decision boundary. And we'll talk about that in a second, right? And so the way that you can go from local robustness to global robustness is to basically say that everything is locally robust, or the model refuses to comment on what class it is. And that's why the decision boundary in this case is so thick, because it can't certify that this particular instance definitely belongs in this class. Okay? That's how you make, that's the sort of conceptual idea for a globally robust neural network. The way that we ended up training these things is actually relatively simple. And so I want to kind of explain the intuition here. So let's imagine here that I give my neural network a piece of information to classify. It classifies it, and it splits it in between 1 and 4 classes. And I'm just looking at the logit scale. Okay? And so I can see that class 1 has the highest value, so the classifier thinks that it's class 1. Okay, so the next class down, right, is class 2. And the claim that we want to make is that if the margin between those two classes is large enough, then a small change in the input, right, an adversary adding a little bit of noise within the epsilon ball, is not going to allow class 2 to surpass class 1. It's that little bit of noise isn't going to be enough to close that gap. Okay, that sounds fine. How do we actually make that happen in practice? So there's this formal idea of smoothness called the Lipschitz constant that tells us how much things can change when you have small changes in the input, right? And it's been known for a while that robust models are actually smoother, right? So they have smaller Lipschitz constants, right? And so if we can make a model that's robust, we can drive down the Lipschitz constant enough that we can actually say things like this, right? That it's not going to change very much. A small change means that it's going to go down the top class is going to go down just a little bit, and the other classes are going to come up some. But if we add those things together, it's not going to go past it, right? And so we add this new class, which we call the bottom class, which reflects the highest score an adversary can get relative to the top class. And so now what you can do, as long as you do the two things, you make sure your model is smooth, you quantify how smooth your model is, and then for a small change, you figure out what's the worst it could be, and then you just train your model to drive down that bottom class, right? To make sure that it's always classifying correctly. Okay, so how well does this work? Basically, it works pretty well on 2 benchmark data sets. We're either exceeding or matching the previous state of the art, and that's good that we're doing well. But that's not really where the technique shines. Where the technique shines is in terms of its performance, right? So The GloRNet certification and training is significantly more time and memory efficient than other methods and far more scalable, right? So it's taking far less time and it's taking far less memory to actually do. And so that suggests to us that we'll be able to push this beyond these sorts of very simple benchmark data sets that are often used for certification research and into larger data sets like ImageNet that is future work. Okay, so that was our little science piece where we dove into that particular paper. The next thing that I want to talk about is I want to talk about some of the tools that we've been developing and that we've released. Specifically, there's a tool called Juneberry that we've released recently to GitHub. So what's Juneberry? The idea of Juneberry is that it provides a framework for reproducible machine learning research, right? The idea is not to have yet another framework that makes you go fast. This one is a framework that lets you go carefully and reproducibly, right? And so it improves the experience of machine learning experimentation because now things are far more reproducible and I can dial in on the different pieces that I'm trying to do, right? It's extensible for a variety of machine learning tasks. And the way that it basically works is that we have all of these different adapters for the different pieces, the different backends. So we support PyTorch, Detectron2, MM detection, and TensorFlow, right? And the idea here is that what you can do with Juneberry is you can make a table of results more easily for your papers. And so some of the documentation that we've released includes this vignette where we replicate a classic machine learning result, and it walks through how we're going to load the data, how we're going to build a model factory so that we can take some machine learning component that exists and bring it into Juneberry, how we can in fact fill out a config to replicate a training strategy from a paper, how we can train a model, evaluate a model, and then how we can change the little pieces in the config in full factorial experiment or other experimental design if you want to implement that, and just literally get all of the results and have your little table of results, right? And additional vignettes are coming for other pieces. Okay, so to sort of come back, the DoD needs secure AI across multiple policies. Train but verify is taking two of those, doing the right thing and not revealing secrets. And the idea is that we're going to allow for the use of high stakes, or we're going to allow for the use of sensitive data in high stakes environments. What we've done this year is basically a lot of pushing the state of the art and understanding how we can measure how much information is leaked and releasing some tools. And next year what we're going to do is we're going to develop training methods for do and reveal that either enforce both of those policies or have a principled trade-off between them, as well as releasing additional tools. I'd like to close the talk with a sort of slide that shows the team. We're a big team. There are a lot of folks that have done a lot of work here. I specifically just called out the PIs, myself, Andrew Mellinger, my co-PI. He's sort of the guiding force behind Juneberry. Three of the professors on campus, Leo Bauer, Matt Fredrickson, and Brian Parno, as well as a collection of additional technical staff and students. So thank you, everyone. I hope you enjoy the rest of the day.